welcome to my presentation on chromium color reactions with students. So, why would chromium be good for color reactions? It was first discovered in 1797, and it derives its name from the Greek word for color, which is chroma. That's because its compounds produce a wide range of colors. So that's great for these kind of color reaction demonstrations. Got an electron this is an electron configuration, and it has 3 common oxidation states: 2+, 3+, 6+, and that's along with its the colors associated with those oxidation states. And there are a lot more colors that chromium can be, but these are the common ones. So I have a criteria for what good reactions would be. Obviously, they have to have colors, and the methods are going to be simple, or simple enough for the age of the student. So that's A-level students for outreach, first year chemistry, foundation year chemistry. They can't be too expensive. The chemicals can't be that expensive. Neither can the equipment. Can't be complicated or expensive equipment. Basically, it can just have to use stuff found in the teaching lab. They can't take too long. There's certain time restrictions, so they have to be able to be done in an afternoon or at most a day. And the chemistry has to be simple but interesting. So these are the reactions that I'm going to be doing, covering this presentation. So chromium reaction that takes place inside of a breathalyzer. You can sort of scale it up, do it in a flask. That's quite interesting. The ammonium dichromate decomposition, or the ammonium dichromate volcano, as it's called sometimes. And then a potassium dichromate reduction, chrome yellow synthesis, and a lead-free alternative to the chrome yellow synthesis. So the first reaction will be reducing chromium. This is the reaction that takes place inside of a breathalyzer. One of the reactions is ethanol. So when you breathe into the breathalyzer, if there's alcohol in your breath, the dichromate should react and turn green. And that's the reaction scheme there. As you can see, it's redox. The ethanol is obviously oxidized, and the chromium is reduced. And it's simple and has an interesting real-world use that I think students would like. These are the methods for the first reaction. So you add 10 ml of sulfuric acid to a flask, 0.9 ml of potassium dichromate. A solution is added. Then you add a ml of ethanol, and you see a color change. You should see green. And then you dilute this solution. If you wanted to UV vis, you add it to some water. You add some of it to some water, and then you can put that solution inside of a cuvette, and then use the vernier UV vis spectrometer, and then you can record the wavelength that's emitted at the highest absorbance point. So these are the hazards and disposal routes for this reaction. Sulfuric acid is corrosive, so wear gloves, and you dispose of it in the aqueous waste. Potassium dichromate 0.1 molar solution, dissolve in the aqueous waste. It's toxic, carcinogenic, and corrosive, so you always wear gloves, and it's a strong oxidizing agent and harmful to aquatic life, so just make sure you dispose of it correctly. Acetaldehyde, disposed in the aqueous waste, add some water. Acetaldehyde is what's made after the ethanol reacts. It's flammable, carcinogenic, and toxic, so gloves. And then the chromium oxide it's in the aqueous waste. It's non-toxic. The cost of these chemicals: so sulfuric acid is cheap; it's a common chemical. Potassium dichromate isn't too expensive, I'd say. I saw 500 grams being sold for like £65, and you don't use it that much for this reaction, so it's not too expensive. It's not harmful. The second reaction is the ammonium dichromate decomposition, or ammonium dichromate volcano. This is the reaction scheme. The chromium 6+ reduces down to chromium 3+. And it's quite an exciting decomposition reaction. This happens because the ammonium dichromate is quite a good oxidizing agent. But you don't have to stop there. You can reduce it even further down into pure chromium metal. You do this by mixing it with some aluminium powder, lighting it on fire, the match, and that should give you chromium metal and aluminium oxide. So these are the methods for that reaction. First, with the ammonium dichromate, you place 10 grams on a heat-proof mat, then light it with a match, and then to further reduce it, you wait for it to cool, and then you mix it with 3 grams of aluminium powder. Then you light that, you should get chromium metal and aluminium oxide. So these are the hazards for this reaction. Everything here is solid, so it all goes in the solid waste. Ammonium dichromate, it's a strong oxidizing agent, toxic, carcinogenic, corrosive, so wear gloves to dispose of it correctly. The chromium oxide, just non-toxic, goes in solid waste. Aluminium powder is obviously flammable, so be careful around that. And then goes in solid waste. Aluminium oxide also goes to solid waste, and chromium metal. The cost of these chemicals, so ammonium dichromate, I saw you can buy about 500 grams for about £45. It's not too bad. Yeah. Chromium metal. Third reaction is potassium dichromate reduction. Potassium dichromate is reduced down to that chromium oxide, and then it forms a precipitate. So it should go green, and then an even dark green. So that's the first reaction where it's reduced to 3 plus chromium, and then it reacts with water to form that even darker green color. So exothermic reaction, as long as it shows a clear color change. These are the methods for this reaction. So it's quite simple. So you put 7.35 grams of potassium dichromate in a 50 ml of warm water, and then 20.8 grams of sodium bisulfate, 50 ml of water, and then you add the sodium bisulfate to the potassium dichromate, and you should see it go green, and then obviously darker green precipitate. So these are the hazards and disposal routes for this reaction. Potassium dichromate, been over it before, so I'll just move on. Sodium bisulfate, disposed in the aqueous waste. It's harmful, so wear gloves. And the cost of these chemicals, like a bit of a potassium dichromate, sodium bisulfate is extremely cheap, so you can buy a kilogram of it for £6, so it's not bad. Waste. Now, chrome yellow synthesis. I think this would be a good day-long first-year reaction. You start with this green chromium complex, and then you react it with some sodium hydroxide to form a sort of blue silver color. Then you react that with some more sodium hydroxide to form this green color. Then that's reacted with some more sodium hydroxide and hydrogen peroxide, and that forms this bright yellow color, and along with water. And then you react it with acid. You react it with acid in order to get rid of the sodium hydroxide, turn into water. As the sodium hydroxide would react with the lead at a later step, forming lead hydroxide, which you wouldn't want because it would affect the color. So yes, you react a lead solution that you'll make with the chromium, and that should make you a very bright yellow precipitate. There's lots of color change in this reaction. The chemicals are quite dangerous, but you should be able to fine as long as people take appropriate measures to be safe. So these are the methods for the reaction. You react to 0.1 grams of the chromium nitrate. You dissolve it in 10 ml of water. Then you add 8 to 10 drops of 25% sodium hydroxide until the solution turns grey-green, and then green. Then you add 5 ml of 30% sodium hydroxide. You carefully heat that solution. Oxygen is made so it can boil over. A color change is observed as the chromium oxide is produced. Boil this 15-20 minutes, that's to destroy the hydrogen side. The next part, you start preparing the lead nitrate solution. So you mix 0.9 grams of lead nitrate in 50 ml of water. Then you add 3 to 5 mils of dilute acetic acid. Just check until it's acidic with litmus paper. You mix it up until it's dissolved. Then back to the chromate solution. Use UV-vis spectrometer to record the peak absorbance. While boiling, drop wires dilute acetic acid to make the solution orange. Then you add 3 more drops. You can use UV-vis afterwards, so you can compare it to the one before. So before it would just be yellow, hopefully. Then afterwards, because you added the acid, the equilibrium changed, a lot of the orange product is made. You should see a good difference, and you should see at least some of both of them, both the orange and the yellow color for the two complexes. You record those peak absorbances. Then you drop wise at 20 ml of lead nitrate. You boil it for 5 minutes, and the chrome yellow should precipitate. Filter it, dry it in an oven. You can actually make it into paint, so you mix it with linseed oil, and obviously make sure that you clean all of the glassware and table or whatever it is down, because once it dries, it'd be very difficult to get off. These are the hazards and disposal routes for the chemicals used in this reaction. First, the chromium nitrate is dissolved in water, so you just dispose of it in the aqueous waste. It's a strong oxidizing agent and harmful, so you got to be careful with it, especially wear gloves. Sodium hydroxide, aqueous waste again, it's corrosive and harmful, same with the hydrogen peroxide. Lead nitrate is a strong oxidizing agent, and it's carcinogenic, corrosive, harmful, and toxic to aquatic life, so wear gloves, dispose of it correctly. And then the chrome yellow is, obviously, it's carcinogenic and it's harmful to aquatic life, so you put it in the solid waste bin. So the cost of these chemicals, the chromium nitrate, seems expensive. It's 100 grams for 440 pounds is what I saw online, which seems extremely expensive until you realize that for this reaction you only need 0.1 grams of it. That's not too bad. Sodium hydroxide and hydrogen peroxide are common lab chemicals. The lead nitrate is quite cheap also. I saw 500 grams being sold for 20 pounds. Yeah. So this is a slightly less dangerous version of chrome yellow. It doesn't actually involve lead. It's less carcinogenic. So the potassium chromate reacts with zinc sulfate. That makes this orange zinc chromium complex. This complex then reacts with sodium hydroxide to form a very bright yellow pigment, very similar in look to chrome yellow. But there are less color changes, not as interesting as the actual chrome yellow synthesis. But it isn't as dangerous, which is a good thing. Still dangerous though. So these are the methods for this reaction. First you add 4.855 grams of potassium chromate in 25 ml of water. Dissolve it, then add 25 ml of 1 mole of zinc sulfate solution. You should see a colored orange precipitate at that point. Then you add 4.2 ml of 6 mole of sodium hydroxide, and then you'll get your bright yellow zinc chromium complex that looks like chrome yellow. Filter it dry in an oven, and then you can make it into paint with linseed oil or other binders for paint. So these are hazards and disposal routes. Potassium chromate, disposed in the aqueous waste. It's a strong oxidizing agent, toxic, carcinogenic, corrosive, harmful to aquatic life, so wear gloves and dispose correctly. 1 mole solution of zinc sulfate It's corrosive, harmful, and toxic to aquatic life. Same thing, really. Gloves and dispose of it correctly. And then sodium hydroxide, which is corrosive and aqueous waste. The cost of these chemicals, so the potassium chromate I saw being sold 100 grams for like £10. It's not that bad. The zinc sulfate I saw like 500 grams being sold for like £50. And then the sodium hydroxide is just a regular chemical, so that's fine. Thanks for listening to my presentation about chromium color reactions.